Okay, so we're going to have a look at the quite tricky topic of electromagnetic radiation and how that relates to temperature. So what I've got here is a light bulb, and imagine that this light bulb is not turned on. It's a filament light bulb. It's one of those bulbs with a really thin wire in there. And if you looked at that light bulb normally, it would be probably grey. And you might think, well, it's not very warm, it's quite cold if it's room temperature, it's not emitting any heat. You'd be wrong. Every single object that you encounter in your life is emitting heat because it's not at absolute zero. So all objects are emitting infrared radiation, which is known as heat. So even at room temperature, that's the case. And if an object is not glowing, if it's just its normal colour, it's emitting infrared. Now, as you heat an object up, it will emit more infrared, but then something after that will start to happen. So if I turn this light bulb on, you will notice if you look at it, it goes from this wire being grey, when it's not a light bulb because it's not giving out any light, to starting to give out light. But it won't just give out white light straight away. That's why I've chosen this filament bulb, because these filament bulbs show this really well. If you heat up anything, but especially maybe a piece of metal slowly, so think about if you had an iron nail, maybe in a Bunsen burner, it's an experiment that we do at school, it would be grey to start with, but as it heated up, I'm going to increase the heat here, so heating up, it will gradually go from being grey, or whatever colour it is, with just infrared, to start to glow a very dull and then slightly less dull red. As it gets hotter again, it will then go to orange and then to yellow. And you might be seeing a pattern here. If you think about it, grey is it's emitting infrared, and then it starts to emit red, orange and yellow light. What's happening is the radiation it's emitting is travelling this way along the spectrum. Now the next one is green. It won't emit green light, we'll look at that more in a moment. The one after this is white. So objects will glow red, orange, yellow, then white. If you can get it even hotter, think about a Bunsen burner flame, for example, it goes from yellow to, it will go to blue, and then maybe even purple. That's pretty hard to do on Earth, but really hot objects can actually emit UV light, X-rays or even gamma rays, and we see this in some stars, some very energetic stars. So as we increase the temperature of something, the radiation that it emits goes this way along the electromagnetic spectrum. I'm going to increase my arrow. So as the temperature increases, we're increasing. Now if I go from radio to gamma rays, that means I'm increasing the frequency of the radiation, or the energy of the radiation. Like I say, all objects emit infrared, but as they get hotter, they might start to emit visible light, and theoretically, if you got them hot enough, it would go to UV X-rays. Also, very cold objects emit microwaves or radio waves. They're usually objects that are colder than we get on Earth, so we don't really experience them too much. Now you need to know about this relationship a bit more formally for your GCSE, and this is quite tricky, especially if you're learning this quite early on in your GCSE. So we need to know that all objects, every single object you encounter, emit electromagnetic radiation. Now the higher the temperature of that object, the something the intensity, the something the frequency, the something the wavelength. Now we've already seen in this part here that the higher the temperature, the higher the frequency. So the higher the temperature of the object, the higher the frequency of the radiation that's emitted. If you remember, if we increase frequency, we also decrease wavelength. They are inversely proportional. The longest wavelength is radio waves and the shortest is gamma rays. So we can also say that the higher the temperature of an object, the shorter the wavelength. And then finally, intensity. Intensity is how much energy is emitted per second, per metre squared, if you want to be very specific, but basically how much energy is being emitted per second. A higher temperature object is hotter, and therefore you can probably imagine that the intensity of that radiation is higher. Think about if you stand near an open flame, near a fire. As you get closer to the fire where it's hotter, you can really feel the intensity of that flame a lot more. So the higher the temperature of the object, the higher the intensity, or the higher the frequency, or the shorter the wavelength of the radiation it emits. But I've left a little line here, and that line is for me to write peak. because objects don't just give out one radiation, they give out a range of radiations, and we can see that here on this graph. So this is an intensity versus wavelength graph, and we usually see it drawn this way around. And increasing wavelength, remember, goes from gamma all the way up to radio, but I'm just going to focus on the bits we really see here, which is UV, visible light, infrared. And within visible light, it's quite useful if we know which side is which. So UV is violet, IR goes to red, so we'd have Roy, G, Biv, this way. So infrared, red, orange, yellow, green, blah, blah, blah. Now, if we think back to our light bulb, when it's cold, it's emitting mainly infrared. That means the peak radiation, the peak of the curve, needs to be at infrared. So this here is a cold object. This line, it represents a cold object. The peak is above infrared. So this object probably isn't emitting any visible light. It's probably being heated, well, yeah, it'll be heating up. It'll be quite a hot object, really, for this graph, but it's not as hot as a filament bulb when it's emitting visible light. So we can think of it as a colder, let's say colder object, because the peak is above infrared. As we heat the object up, the peak will start to increase in frequency, decrease in wavelength, and increase in intensity. So this here is a slightly hotter object. And we can see that the peak is now just above here, the boundary between infrared and red, and the peak's got higher, the intensity is increased. The intensity is increased and the peak has increased in frequency and decreased in wavelength. Now this this object is giving off visible red light, quite a lot of it, some infrared, we can see that here, and also little bits of orange and yellow. So overall, this object's going to look red, because like the average light is red, as it were. So this would be red hot. Not hat, as that looks like it says, whereas this cold object is not emitting light. Now, as we heat the object up even more, the peak once again increases in terms of intensity. So we've got hotter again. The peak increases in intensity, and we can see now the peak's also moved more towards the centre of the visible light. The wavelength's decreased, the frequency will have increased. And here, this is about in the middle of the visible light spectrum. It's in about green. Now this is why we don't emit green light in very simple layman's terms. When you are at the point where green is at the peak, we're emitting lots of green light, but we're also emitting quite a bit of orange and yellow and red light over here, and we're also emitting some blue and violet light. Now what happens when you mix together green, orange, yellow, blue, violet, red light all together? We get white. So this is when we have something that's called white hot, because it's emitting all the wavelengths of light, because it's white hot. So this is a tricky topic, but as long as you remember this kind of sentence here, all objects emit EM radiation. The higher the temperature, the higher the intensity and frequency, and the shorter the wavelength of the peak radiation it emits, you should be fine.